All right, so for example number 2, or rather number 4, which is the second example. So let's find the equation of a plane given the equation of a plane given this equation for the surface at the given point, also the equation of the normal line. All right. So let's compare these two exercises and see the main differences between the two. And well, the main differences are, well, the way the function is given. Notice in this case we were given an implicit function, so we needed to move everything to one side and call that our big F to get the gradient of, and then evaluate the gradient at that point, etc. So there is another way to find the equation of the plane and all that. When we're given a function that it's explicit, in this case it's z solved for x and a function solved for z in terms of x and y. But it's not my favorite way to go about it, so we will be working everything in terms of implicit functions. So regardless of whether you're given an implicit function or an explicit function, just send everything to one side and call that your big F. All right? So big F will be, well, number one, let me do z. Let me move everything to the left hand side. That's plus x squared minus or plus y squared over 4 minus 9. So that is equal to 0, essentially, if we treat it like an equation. But again, our implicit function is written as a big F, which is equal to 0. So if f equal to 0, well, then also f equals to this implicit function. And let's use this for the gradient. Okay, let's find the gradient. Nabla of f. That is the partials with respect x, with respect y, and with respect z respectively, right? So with respect x, that is 2x. With respect y, that is 1, what is that, negative 1/2? Oh no, it's positive 1/2. Y, comma, 1. Right, so that is our gradient here. And well, so let's next part, let's evaluate the gradient at the point 1, 0, 8. That is 2 times 1, comma 1/2 times 0. Well, there's no z's to substitute the 8. There's just a 1, so it's just 1. All right. So that is going to be 2, 0, 1. The vector 2, 0, 1. All right, and from here, well, we already have everything we need to obtain the equation of the tangent plane to the surface. All right, so again, we use the general form, and then we turn this into standard form. That is ax minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. So, and again, where are these numbers coming from? Well, recall that a, b, and c are the components of the gradient vector, and x naught, z naught, y naught are going to be the coordinates of the given point. All right. Again, this is very formulaic. Just make sure to get the correct implicit function and use the correct differentiation rules. That's where things could go a bit wrong, right? Other than that, I think it's no big deal. Okay, so that'll be 2 times x minus x naught, that is 1, plus b, which is 0 times y minus y naught, that is also 0, right? Yes. And z, which is 1 times z minus 8 equals to 0. So that's going to be a smaller equation, that's 2x minus 2 and z minus 8 plus z minus 8. Let that be equal to 0. 2x plus 2c, it's 2x plus 2z. Plus z, not plus 2c, plus z only. And then minus 10. equals to 0 to x plus z equals to 10. All right? So our equations of the planes do not necessarily have to have the three variables. Actually, you can think of this equation in two variables as a cylinder. Remember those cylinders that were graphed in the direction of the missing variable? So we would graph the xz trace, that is a line on the containing the wall on the x and the z axis and extend it along the y axis. So that's one way to graph it. Otherwise, I mean, just use GeoGebra, of course, all right? So unless you have the three variables, well then peekaboo and get the intercepts and do that little triangle containing the 3 points, all right? Now to get the equation of the normal line, that's going to be, again, it's the usual r of t equals x naught plus at, y naught plus bt, z naught plus ct. And again, where do we get a, b, and c? They're the same as the gradient vector. Let me highlight them so you can see that. Okay. That's the same. And x naught, y naught, z naught, they're given. All right, that's all it is. So, x naught, y naught, z naught. And just substitute, that is r of t, that equals x naught, which is 1 plus a, which in this case is 2t, 0, because they're all zeros here. And what's next? That's z naught, which is 8, plus c, which is 1t, which is simply plus t. All right? And that is the equation of the plane and the equation of the line. I'm not going to use GeoGebra today, so I think if you're curious about how it looks, you might want to do it on your free time, and the same way we did it. If you don't know how to plot the line, just watch the video from the previous lecture where I show all the steps, how to use the curve input and then the limits and the parameters and all that, right? So, okay. So, actually, I forgot to get rid of the example number 5 because I feel like it's repetition of the same. So I'm going to skip example number 5. So I think we should get to linear approximations, which is the second part of the section. All right, linear approximation. So let's discuss or refresh rather what we did back in Calculus 1. Were you guys learning Calculus 1? So for instance, a linear approximation means that you can approximate f of x equals to, or not equals, you can approximate, you can approximate any function to a linear function, right? That's a linear approximation. It doesn't matter. Your favorite function, say e to the x can be approximated to mx plus b. Maybe sine x can also be approximated to a linear function. Square root of x can be approximated to mx plus b under certain conditions. Because for instance, let's look at the first graph right here. Well, this looks a lot like the exponential function, right? So at a very restricted interval, we can approximate this exponential function to a linear function. So that is maybe, if you want the exact value, that's just at the point of tangency. But if you want an approximation, maybe just consider the interval a plus epsilon minus epsilon, so my plus or minus some tolerance value here, all right? And well, what is that width that's going to be? Well, so it depends on your purpose. It depends on how accurate your result should be, But of course, the linear approximation, it's just a baby type of idea to get into the applications of the derivative. But of course, there's a better way to improve these approximations. Any ideas? How do we improve The approximations. It's a Taylor series, right? Remember infinite series from calculus 2? So Taylor series or Maclaurin series, depending on the center. So you use that to get better results. Say you want to approximate, I don't know, the square root of 29, all right? So you would need to guess a function, first of all right? In this case, it's a square root function. And then you would need to center your series at a value that is close to that is the closest to the perfect square that is near 29. That is going to be 25 naturally, right? So you don't want to go all the way to 36. So 25 is going to be more than enough. But of course, that's going to give us a linear approximation. And well, to approximate the square root of 29, which is 4 units away from 25, well, we can already tell that the approximation is not going to be the best. However, if we wanted to evaluate, or rather approximate, the square root of 26, well, even just a linear approximation is going to be fair enough because 26 is pretty close to 25. Of course, you're not going to use a power series or a linear approximation. Rather, at 64, even though 64 it's a perfect square, no, that's not going to work. So you need a number that is closer to the number you want to evaluate. Now, but of course, I mean, to come up with a way better approximation, you would use maybe a quadratic approximation, a cubic, a quartic, a quintic, etc. Well, what is that? Again, Taylor or Maclaurin series, depending on the center. But in this case, well, we're just going to limit to linear approximations. All right, that's going to be more than enough. All right, so again, for this square root of 26, for instance, so you would need to guess f of x equals to the square root of x and center it at x equals to 25. Now, if you wanted to evaluate the square root of 67, for instance, you would need to come up with a new linear approximation, not center at 25, because 67 is too far away from 25. So the closest perfect square to 67, isn't that 64, all right? And so on. I mean, I think you guys are familiar with this process, right? Approximation. All right, let's put 3D glasses to this linear approximation. But in this case, instead of evaluating, or rather approximating using the linear approximation, which is nothing other than the tangent line that you guys know how to get, this time we're going to approximate using a tangent plane, because now we're going to evaluate or approximate function values that are related to functions of 2 variables, and potentially 3 variables or 4 variables, doesn't matter, right? But in this case, rather than approximating this to a tangent line, it's going to be to a tangent plane. All right? So, and again, how do we get that linear approximation? Well, so because this is really mx plus b, how do we get m? M, which is the slope, that's the derivative, isn't it? And then that x minus a, that's the variable term, the variable factor rather, plus the independent term f of a, which is the y-intercept in this case. All right, how do we extend this to multiple variables? Well, so L of xy, which is this time going to be the equation of a plane, not the equation of a line. So to see this x minus a, we're going to have a y minus b, that's the y term, and an independent term. The independent term is going to be the value of the function at the point AB, that's the z value. You could think of the z-intercept. I don't like the z-intercept thing anyway, but I think you get the idea, right? So, but then we have f subscript x and f subscript y. What are those? Well, partial derivatives. What do the partial derivatives give? The slope as well, right? The slope in the x direction, in the y direction. Well, that's what we need. That's what we need to make it 3D, right? So, let's see. Let's find a linear approximation Let's have a look at one example. Find the linear approximation to the function f of x y equals to 10 minus 4x squared minus 3y squared at the point 1, 2. Then use it to express, or rather to approximate the value of the function at 1.1, comma 1.99. You know, the equivalent of evaluating, say, the square root of 26, the square root of 63, or 83, or something like that, right? Okay, so number one. So we need partial derivatives, right? So we need the changes in with respect x and with respect y. Those are the two slopes. So we're going to use the gradient because, again, the gradient, it's like a database, if you will, that stores that information, the rate of change in the x direction and the rate of change in the y direction. All right, so let's find nabla of f, that is the gradient, which is a vector. Don't forget the arrow here. It's a vector, not just a scalar. That is the partial of f with respect x, that's negative 8x, and the partial of y with respect, partial of f with respect to y, that is negative 6y. All right. So let's evaluate nabla of f at the given point 1, 2. So that is our center value. You know, let me actually do this so I can relate with the idea from before. All right. So let's evaluate this to at negative 8 times x, which is 1, and negative 6 at 2. That is negative 8, negative 12. Now, what are these numbers? Well, these are the slopes in the x direction and the slopes in the y direction. That is, this negative 8 is the slope, and this negative 12 is the slope right here at the given point. All right? The terms x minus a, y minus b, so the a and b are the 1 the 1 and the 2. All right, we're going to get that in a second. And we also need to find the function value at the point 1, 2. That is, we need to evaluate f of a, b. How do we get f of a, b? Just substituting the original function. That is, f of 1, 2, that equals 10 minus 4 times 1 squared minus 3 times 2 squared. That is 10 minus 4, in this case, minus 3 times 2 squared, which is 4. 3 times 4, that equals to 12. That equals negative 6, right? Which is, in this case, the f of a, b term, all right? That's the f of a, b term. Okay. Looks like we have everything we need to write our linear approximation. So again, our linear approximation L of x, y, approximating this to a plane, that is f sub x at AB, x minus a. So I'm just rewriting the formula for now. F sub y, a comma b, at AB, y minus b plus the function value. The function value is given by what we just got, all right? The next is just evaluating, just substituting. That is, and this is not equal to. Rather, this is approximately, right? It's approximation. L of x, y. So the derivative, that's negative 8 times x minus a, which is 1, plus minus 12 times y minus 2 plus a function value, which is negative 6. So it's all minuses here. It's a bunch of minuses here. All right? So that is our linear approximation. All right? So that means we can use this linear approximation to find the value of the function for points that are fairly close to the given point 1, 2. Like in this case, we want to approximate the function value 1.1 comma at 1.1, comma, what's that? 1.99. Of course, this approximation wouldn't be good enough. For instance, if we wanted to evaluate or approximate the value, the function value for 3.7, and maybe, I don't know, negative 2.3, right? So we would need to come up with a linear approximation at another point, maybe 4. That's the closest integer to 3.7, and the closest integer to negative 2.3. How about negative 2, right? At negative 2. So that's just for a better approximation, of course. All right? Okay, so let's approximate. Oh, let's approximate 3.7, comma, negative 2.3. That is negative 8 times 1.1 minus 1 minus 12 times 1.99 minus 2 minus 6. All right? And after simplifying all this, that should give us approximately negative 6.68. But again, that is just yes.
In the parentheses, you have L of 3.9.
Oh, yes. I don't know why. Yeah, that's the example I made up, right? Yep. The what if, right? No, that's 1.1, 1.99. Thank you. So that's what they're going to give us. Of course, if you want to obtain the exact value, just evaluate at 1.1 and at 1.99 for x and y respectively in the original function. All right? So that's actually going to be the next part, the increments and differentials. That's so we can see what's the actual change between an approximated value and an actual value. All right. So again, this is going to be from calculus 1, and we're going to extend it to functions of 2, potential 3, 4, as many variables as you want. Okay, so the differential for a function y equals to f of x. Yes, so first of all, when you learn about derivatives and you use the f prime symbol, then you also use the Leibniz notation, that is dy dx. But that dy dx was just used initially as a symbol that denotes a change of the dependent variable with respect to the independent variable. Then you saw it as a quotient between two quantities, dy dx, and then you use that to describe these differentials. That is, now we call the differential of y simply dy, which is given by what? Dy equals f prime dx. How come? Because, okay, if y equals f of x, then dy dx, take the derivative on both sides, that's f prime of x. So now we would need to see this as an equation. Solve for the y variable, for the dy rather, by multiplying both sides by dx. Well, so that gives us the differential. And that's actually one of the most important tools to get into the integration, to do the inverse operator of the derivative, which is the integral. Or actually, that's for those of you who may have taken differential equations. Well, we are essentially solving a differential equation by separation of variables. So that's one of the very basic methods that we learn in that course, right? So here is the thing. So when we are looking at this increment, so we're centering a function at a value, and we may increment or decrement, if we will, by a positive or negative, respectively, kind of value. So we call these increments, let's call this delta x and delta y. Okay, let's call them like this. However, well, what's the picture anyway? So going back to the idea from calculus 1, we have this function like this that looks like this, right? And we have this tangent line. It's just touching at one point. And then from here, well, so the idea is to go from a finite number of changes, right? That is what we're gonna call our delta x and our delta y. But what we allow in this case to have delta y to be equal to dy and delta x to be equal to the x just for the sake of the approximation, right? So that's how we get this idea of an approximation. Now, but how do we do this with functions of multiple variables? Well, let's recall how do we do this increment with functions of a single variable. That is, so we usually go like delta y equals to f of x plus delta x minus f of x. So for instance, if you want to see the increment in the value of a function, well, you're evaluating, well, actually, if we think of this as an application, for instance, when you are finding the volume of a sphere, for instance. So one of the applications for derivatives is to look at increment. That is, what would be the effect of changing the radius of the sphere by just 0.1 unit? In other words, how much would the volume change if we just modify the radius a little bit, So, and well, then we would compare with the original value, find the percentage of increment and a bunch of things. Well, so that increment, it's going to be given by f of x plus delta x, which could be plus or minus. Maybe instead of increasing the radius of a sphere by 0.1, maybe we decrease it by 0.2, So that number can be potentially negative. And then we subtract the actual value, right? Well, extending this to functions up to variables, so the f of x plus delta x becomes f of x plus delta x comma y plus delta y, because now we're incrementing, or well, rather changing the two variables at the same time, x and y, and then we subtract the value of the function value, of the original function f of x, y. All right, so this is going to give us the actual change, right? But of course, we may want to look at the at the approximated change. How do we approximate the change? Again, this idea about differentials, when we look at this, dy equals the derivative times the delta x. Well, in this case, we allow those deltas, which are finite values, to be equal to the infinitesimal values dy or and dx, of course. However, if in this case we're just looking at the change of the independent variable, one independent variable, to see what's the effect on changing, how that changes the dependent variable, well, in this case, so if this part right here looks a lot like dy equals f prime of x dx. However, we will no longer formulate this like this. Now we're going to look at the change of the dependent variable z when we change both variables x and y simultaneously, right? And in this case, what do we need? Partial derivative to see what's the change with respect x and the change with respect y. And the changes in the x direction, the changes or increments rather in the y direction. All right? So all we're doing is just adding one more term or two terms or three terms depending on how many variables our function is. All right, so let's have a look at one example to find the total differential. So we're not going to do the increments yet. First, we're going to get some practice with finding the differentials. So the differential of the function w that depends in this case on three variables x, y, and z. Okay. So what do we need here? So in this case, dw. So w changes. We're looking at the total differential, not just at the partial change. So that is, so dw changes with respect x, with respect y, and with respect z. That is, in this case, we need to find the partial of w with respect x, partial of w with respect y, and the partial of w with respect z. Okay, so let's find the partials here. So dw, that equals, okay, the partial with respect x. So what do we have? The first two terms contain x, the derivative of x, which is 1, that is cosine of y, plus the derivative of e to the xy, which is number 1 itself, e to the xy, times the derivative of the exponent xy with respect x, which is going to be 1 times y. Times y. So that'll be y. That multiplied by the x plus negative, okay, the derivative with respect y, oh careful, the derivative of cosine, which is negative sine, times the x, the coefficient x, plus the derivative of the exponential with respect y, that's itself, e to the xy, times the derivative with respect y, which is 1 times x, which is just x. That's dy. And finally, the partial change with respect z, well, in this case, it is just differentiating the z cubed. That is 3z squared dz. So that is our total differential. So here, essentially, we're listing all the changes, not just the change in the direction of x, in the direction of y, or in the direction of z, but all of them. All right, and we're going to use, we could use this expression to potentially see what's the change, or what's the total, or what's the effect of having increments or decrements in x, y, and z respectively. All right, so that's what the next problem is about. So here we're going to find a. All right, so we will use the differential dz to approximate the change in the function z equals to the square root of 4 minus x squared minus y squared as xy moves from the point 1, 1 to the point 1.01, comma 0.97. So here the tricky part is to figure out the deltas, the increments or decrements potentially. All right. So number 1. So let's identify our dx. Again, our dx, it's allowed to be our delta x. We can use our delta x to be our dx because, again, we're approximating. We're just approximating. All right? And that dx, delta x, well, how many units are there in difference from between 1, rather, and 1.01? Isn't that 0.01? But careful with delta y. For delta y equals, okay, how many units to go from 1 to 0.97? Negative, right? Because it's decreasing. It's a decrement this time. That is negative 0.03. Okay? All right. Now it's time to get the partial derivatives. But first of all, let's write the function in a more convenient way. 4 minus x squared minus y squared to the 1/2. So we can easily use the chain rule. Okay? So that is partial of z with respect x equal to, by chain rule, 1/2 4 minus x squared minus y squared to the negative 1/2 times, careful, by chain rule, the derivative of the quantity in parentheses with respect x, which is negative 2x. Okay, so divide out the 2's. Rewrite the function with radicals. So number 1, we're going to be left with this negative in the front. This x remains at the top. And in the denominator, well, if we write the parentheses factor in the denominator with positive exponent 1/2 and then change it to radical, that is the square root of 4 minus x squared minus y squared. Alright, so that's the partial derivative with respect x. For the partial derivative with respect y, well, it's essentially the same process, which all we need is to change this x with a y. So that's not going to change that much. So that'll be y divided by the square root of 4 minus x squared minus y squared. Alright, so we have our partial derivatives. Now, let's set up our expression that calculates the total change. Okay, and then compare with the actual value. So first, we're computing, what's that? The approximated value using derivatives, and then we're going to compute the actual value. All right, so the total change, dz, equals to the partial with respect x dx plus the partial with respect y dy. That is the partial with respect x, which is what we just got right here. That is negative 1 over x, or rather x, over the square root of 4 minus x squared minus y squared dx. And in this case plus, but rather minus, because the partial derivative with respect to y is a negative term. Y over the square root of 4 minus x squared minus y squared dy. Okay? So that is the expression that will calculate the approximated change. Now let's substitute the values to get that approximate change. Okay, so so dz equals to negative, what's x? X and y are going to be our x and y here, 1 and 1. Okay, so that is negative 1 over the square root of 4 minus 1 squared dx. But, well, dx, which is allowed to be the delta x, which is 0.01. Minus y, which is another 1, over the square root of 4 minus 1 squared. That equals times delta y, but careful, don't forget that it's negative, because it's going from 1 to 0.97. That is, it's not an increment, or it's actually going a smaller value. All right. Okay, let's simplify this a little bit. Well, let me just do negative 0.01 divided by the square root of 2 minus, what's that? Actually, that's a plus, 0.97 over also the square root of 2, which in this case, that is approximately 0.014. Right? Yes.
Instead of
0.03. 0.03. Yeah. 0.03. Yeah, I was still thinking of the actual number again. So that's the approximated change, taking partial derivatives, creating this huge expression to find the total change. But what about the actual change? The actual change that involves simply deltas here. Well, so let me call this the actual value. So for the actual value, what is it? The incremented value, that is f of x plus delta x, comma y plus delta y, minus the original value of the function. Okay, let's see what is this. So in this case, the x plus delta x will be taking into account for the entire 1.01. So that is 1.01, because x is 1 and the delta is what? It's 0.01, isn't it? So it's going to be all the 1.01. And In this case, what is that again? That is 0.97. Because delta y, that is the increment, it's negative by 3 units, so it's 0.97. And what's x and y? X and y are going to be 1 and then also 1. So what do? The original function, without finding any partial derivatives, by the way, that is the square root of 4 minus 1.01 squared minus 0.97 squared minus the value of the original function. That is the square root of 4 minus 1 squared minus 1 squared, which we already calculated it before, right? So what is that going to give us? Well, this is actually equal, well, approximated to 4 decimals, 0.013.7. Compare the two results. Is the result obtained using the partial derivatives a fair approximation? I mean, yes, or maybe not, depending on the purpose, depending on the margin of error that you're applying this, maybe in the manufacturing of parts for cars or electronics, maybe that that additional 0.0003 can blow up the whole system. Who knows, right? But I mean that at least for the sake of visualizing the idea, I think it's a good approximation. All right. Do we have anything else? Oh, another application to chemistry, and let's wrap up this section. Okay. So what do we have? The pressure, volume, and temperature of a mole of an ideal gas are related by the equation PV equals 8.13 T, where P is, again, measured in kilopascals, V in liters, and T in kelvins, in degrees Kelvin. Use differentials to approximate the change in the pressure if the volume increases from 12 liters to 12.3 liters, and the temperature decreases, careful, from 310 Kelvin to 305 Kelvin. Yes, the problem looks similar to the one we did when we did the, what was that? Number one, the derivatives, the partial derivatives, to explain the changes in terms of rates of changes, you know? And then number two, we did this for the chain rule, to see what's the total change or what's the effect on changing everything at the same time. But this time, we want to know if the value of the pressure will increase or decrease by manipulating these changes right here. All right? Okay. So, all right. So number one, let's write the equation in a more convenient way. That is P equals 8.13 T V to the negative 1. All right? So from here, we're going to take the partial derivatives again. So let's find the total differential of the pressure, that is dP, which is a term describing a change in volume plus a term describing the change in the temperature. Well, those are multiplied by the partial of the pressure with respect to the volume, all right, and the partial of the pressure with respect to the temperature. All right. So notice in this case, we don't know the rates of change of the pressure with respect to volume and with respect to temperature, because it's not that kind of situation where we're looking at the rates of change. It's not a chain rule problem. Looks kind of similar, but it is not, unless everything were changing with respect to T, right? Like that kind of chain rule problem. But this is not the case. Let me go back. Let me backtrack. Rid of this so you can see the difference, right? And actually you can see the difference in the wording. We don't know, no units of time are there. All right, no units of time are there. Okay, find the partial derivative of the pressure with respect to volume, that is negative 8.13 T V to the negative 2. Well, actually let me write it as, well, let me do, V to the negative 2 dV plus partial of the pressure with respect to temperature, that's just 1 times 8.13 v to the negative 1 dt. Okay, so let's clean this up a little bit. Why not? So that is negative 8.13 t over v squared dv plus 8.13 over v times dt. Again, no time involved here. It's just the effect of modifying both volume and temperature simultaneously, maybe increasing both, decreasing both, or increasing one and decreasing another one. In this case, it's the latter case, the increasing one and increasing one and decreasing another one. Let's figure out those delta V's and delta T's. So number one, our dV, which is our delta V, allowed to be our delta V. So to go from 12 to 12.4 12.3, that is 0.3, right? And to go from 310 Kelvin to 305 Kelvin, careful, our dt, which is allowed to be our delta T, that is negative 5, all right? So the signs matter here. If it's increasing, positive. If it's decreasing, it's negative. Okay? All right, let's substitute the values. That is 8.13 over v squared. So the volume, which is, so in this case, the initial volume, which is 12. Wait, the temperature, which is 310 over the volume, which is 12 squared, plus 8.13 over the volume, that's another 12, times, oh, I forgot the differentials, right? Okay, so let's multiply this by dV, which is 0.3, and by negative 5, all right? After simplifying all this, just use your calculator to get the following result. So dP, it's approximately, all right, negative 8.829 kilopascals. In this case, let's put units. We save the units for the very end. All right, kilopascals. So that is by making these changes, that is increasing the volume and decreasing the temperature, the pressure actually decreases, right? There's a decrement in the pressure, all right? Okay, but of course, I mean, that's just the approximate change. So if you wanted to get the actual change, just evaluate this function at the incremented values, that is 12.3, 305, minus the function evaluated at 12, 310, like we did it in the previous example. All right, but in this case, they're only asking us to get the approximated result, not the actual change. All right.